All right, welcome back. We're doing part three of this bullshit exam, and the plan is to get through 48 all the way to 79. So it's gonna be like solid 20 questions. With that being said, I'm gonna straight up say, as of today, 10/9/22, I don't know how to do 47. I'll have to go back to that in part four once I figure everything else out. I might not get it. It's something to do with molecular balances, and to be honest, that's not my strength. Ironically enough, for chemical engineer, it should be your number one strength. But if you went to IIT, you know the brutality of that first intro class. So I got to go back and study a little bit more of that. Okay. With that being said, I have count them 1, 2, 3 goddamn sheets of paper that are full of back and forth notes that will go off. With that being said, we'll begin. It's going to be a fun little ride. I have my pen, I have space, and I end the monologue. Let's get this shit started. Okay. So it says a desire to burn liquid propane C3H8 with excess air, both supplied at 25 degrees C. Assume that air is 21% volume and oxygen, and the balance is nitrogen. So in other words, 79% of that shit is nitrogen. If 1 mole of propane is burned with X moles of air, how many moles of oxygen appear as combustion products? Okay, first thing we need to realize is pretty simple. It is desired to burn liquid propane with excess air, and it should be key what appears in combustion products. So combustion is a reaction in chemistry that should be pretty easy to recognizable. The products are always going to be carbon dioxide and water, and in the reactants, you're going to be reacting with whatever the question tells you in oxygen. So that's going to be important. The first two things to understand in that whole sentence. So you should immediately think propane, which is C3H8. It's going to be reacting with plus O2 because that's a combustion reactant, and it will always yield carbon dioxide and water. Basically, that's combustion in a nutshell. The next step for you is to balance this chemical reaction, and then that should be really basic chemistry. Remember, just make sure everything comes out the same. What comes in has to come out. The overall stoichiometry of both sides has to match. And if you need a review on that, then come talk to me. I'm just gonna fill them in. I could go through it, but we all graduated, so I would assume this part's easy. So I won't waste our time figuring that little part out. But make sure you balance your equation. So it'd be 1, 5, 3, and 4. That's your balanced chemical equation. Now, what else? Saying if 1 mole of propane is burned with X moles of air, how many moles of oxygen appear in the combustion products? At the end of the day, what this question is saying is you're starting with X amount of moles of air, which is 21% oxygen, as a reactant. When you produce the products, how much of that air that you started off with is finishing or coming out? That's the question it's coming with. So in your head, you should say, oh shit, so our basis of calculations has to be X moles of air. And they're also telling you if you use 1 mole of propane. Well, if you were to use 1 mole of propane, C3, in your guys' head, you should immediately know, based on the stoichiometry of the reaction, you're going to use 5 moles of oxygen, just based on stoichiometry, 1 to 5. Now, going back to the original starting point, we have X moles of air. And this is your starting material. We also know that 21% of the starting material is oxygen. So you have to multiply this whole thing by 0.21 mole percent of O2. Now, this is going to give you X 0.21. This is your mole of O2 starting material. Now, this is how much you're starting with your, how much your entire reaction is starting with. Now, put everything together. If you're using 1 mole of propane, you use up 5 moles of oxygen. If your starting material is X times 21.1% mole of O2, then at the end of the reactant, or when this whole reaction goes through, how much do you have left? It's simply taking the difference between the end material, excuse me, the starting material and the end material. And you'll rewrite all of that as X 0.21 minus 5. Because we started off with 21% of air in the system, and you ended it by using up 5 moles of air. And this X could be as high as it wants. It doesn't really matter. And this will be your answer. That's how much will appear of oxygen once the reaction goes through. Hopefully that makes sense. Okay. 49 states low energy gas is burned in a furnace with excess air. The feed rate is 2,500 meters cubed per hour of gas at 0 degrees C and 1 atm. The amount of air supplied per 100 kilomoles of dry flue gas is most nearly blank. Okay, so there's a couple things you need to realize here. One, question is asking how much air for 100 kilomoles of flue gas is being used. So that should be key number 1. They're giving you a basis of flue gas, which is great. They give you a basis of 100 kilomoles of dry flue gas. Now, how do you relate this entire thing to, well, air? Well, if you guys remember in the last question, they said there's 21% moles of air and 79% moles of N2 and just regular air that we breathe and talk about. In our case, how can we relate the two? Well, we have flue gas, we have kilomoles of dry air, and we also have the molar composition of N2 in the flue gas. So let's put everything together. If we have 100 moles or kilomoles of flue gas, this is flue gas, and since my pen's being dumb, I won't write the whole thing, but 100 kilomoles of flue gas. The composition of it is 84.4% of N2. And this is going to give you a composition of 84.4 kilomole of N2 in the flue gas. That's how much is in the flue gas. Now, remember, this system is surrounded with flue gas and regular air from the atmosphere. So we can do a simple nitrogen balance between the air and the flue gas, and we can do a nitrogen balance with the nitrogen in the regular air and the nitrogen within the flue gas. So basically, what we're going to say is, in our flue gas, we have 84.4 kilos or kilomoles of N2. This is your flue gas. And we're going to set it equal to the feed rate of your air. And we're looking for the molar flow rate of air. But we also know, based on the last question, that in regular air, it's 21% oxygen and 79% N2. So it's going to be 0.79 N2. That is just a mole balance between nitrogen in the air and nitrogen in the flue gas. You solve for your N dot of air, and that's going to give you 101.3 kilomoles of air. Just to really recap, the flue gas is the system. You have 100 kilomoles of it, gives you a basis of nitrogen. You can find the amount of nitrogen in your flue gas. Then you, being smart engineers, say, well, nitrogen balance can be worked out because air has nitrogen and the flue gas has nitrogen. Set those guys equal to each other. In your head, you have to know that 79% of regular air is nitrogen and solve for the molar composition. And you'll notice that all of this stuff here, useless. Just a lot of words to confuse you. Remember, you're trying to work quickly and answer these things as fast as possible. Okay, so 50. It says 19 weight percent of NaO of sodium hydroxide solution is made up by diluting 500 kilos per hour of 50% NaO solution with the appropriate amount of water. The heat of dilution causes the resulting 19%. That's important. It says the heat of dilution causes the resulting 19% of a hydrogen or sodium hydroxide to warm up to 50 degrees. The heat capacity of the 19% weight solution is 3.77. And the rate kilojoule per hour at which the heat must be removed for the solution to cool to 30 is nearly blank. Okay. So they give you a heat capacity, they give you a rate, and they also give you what is the heat removed. Your thermodynamics brain should immediately be thinking of one equation and one equation only, and that is Q is equal to Cp delta T m dot. And that's it. That's the main equation for this. But what is m dot, first of all? Well, m dot, according to the equation, is the resulting 19% weight solution, 19% weight, the 19 weight percent solution of NaOH. Now, the next thing you got to think about is how the heck do I get that? Well, it's not as hard as it seems. It's kind of just thinking of M1V1 equals M2V2 in a dilution, kind of in basic chemistry. The manual calls it no, the manual doesn't call this. They call this sodium hydroxide balance between solutions. I like thinking about it as just an M1 equals M1V1 equals M2V2 from general chemistry. It makes the most sense because what's coming in, I'm going to say M1V1 equals M2V2. And in this case, we'll have 500 kilos of 50 weight percent equals the solution you want, which is 19%, multiplied by X, which is going to be the resulting kilos. This would be M, and then this would be V in your case. And in your weight percent, or excuse me, your molarity, which is in this case kilos per hour, would become 1,315.79 kilos per hour, which is great. Now, you're looking for the rate of heat lost. Now, it's easy. Just use your equation mCp delta P. So here, you would take that 1,315 kilos per hour, multiply it by your Cp, which is 3.77, and then you multiply by the change in temperature, which it starts at 50, and you're looking for the heat that cools at 30, so it'd be final minus initial, 30 minus 50. And it'll give you a negative number, which makes sense because you're looking for the heat that has to be removed from the system. Just absolute value that shit, and you'll get the right answer. It's going to become 99,210 kilojoules per hour. And that makes sense to answer D. Now, remember, in this whole case, the hardest part here was figuring out in your head to get the weight or the molarity or the concentration or the mass of the 19% weight solution. And that's how you always do it. Just think about it as a simple dilution, and the rest is just basic thermo. And that's all for that question. Okay, 51. And if you see me walking around with these papers, it's because I did these in separate moments and I didn't want to rewrite them. Okay, so 50 says 75 tons per hour of calcium carbonate with 9.3 moisture is to be dried in a rotary dryer. 30% of the existing dryer is recycled back to the beginning of the process and joins the incoming moist feed into the dryer. If 68.5 tons per hour of the product is produced, the percent moisture of the dry product exiting the dryer is most nearly blank. Okay, so there's a couple things that are important. It says, A, coming into your system, there's the 75 tons per hour, and its moist percentage is 9.3. That's how much of it is wet. coming out of the system, this product is quote unquote dry. It's dry. And it's saying, what is the moisture percent of the dried product coming out of the reactor? Well, that's easy. Everything in the middle here is to throw your game off. Because remember, in mass balances, especially if it's just a mass in and mass out, you can care about the stuff in the middle if you decide to include it into the stuff you're taking a mass balance to. Again, we're smart engineers, and instead of doing that, we're going to take a mass balance of the whole system, where we don't have to pay attention to that 30% recycle rate, and we don't have to pay attention to any of the math that goes in there. Rather, we can pay attention to the products coming in and the products going out only, which makes our lives easier. Since they gave us a moisture percentage, we do 75 times 9.3%. We're going to get the product that's moist coming in as 6.975 tons per hour wet. What's coming into the system dry is 75 minus that 6.9, which is essentially 68.025. This is dry product, tons per hour. Now, the reason we say to look at what's coming in, or the overall mass balance, is because what's coming in is coming out. You can see the distinct difference. What's coming into the system dry is this number, 68.025. What's coming out of the system, quote unquote dry, is 68.5. Now, clearly there's a discrepancy, and that has some type of water weight to it because it's higher than the dry mass coming in. So you're smart. You're going to say, I'm going to do 68.5 tons per hour coming out of the system minus the 68.025 of the dry product coming in. This is going to get you a number of 0.475 tons per hour. That number here is the wet product coming out of your supposed dry system. Now, the next easy part is the question. The question is asking, what is the moisture percentage of the dry product? Well, you being a smart guy, you're going to say 0.475 divided by 68.5 times 100 is your wet percentage. And that's going to give you 0.693%. In other words, B. And that's it. It's a lot of words to try to confuse you. That's what I've noticed in the majority of these things. Not hard, just having to understand and read what they're giving you. Now, 52 is annoying. 52 says a large pipe carries steam. The outside of the pipe surface is 200 degrees. For personal safety, the pipe is insulated, so the temperature of the external surface insulation is less than 45 degrees. Neglect curvature and apply the following data. They give you the thermal conductivity of insulation, the combined radiation conduction coefficient for the pipe, the surroundings of the air temperature, and the thickness of the insulation is most likely blank. Okay, so first things first, what is conduction? Conduction is the transfer of heat energy by direct contact. The two things are touching and the transfer of energy is happening. That's conduction. Convection is the movement of heat by an actual motion of matter. So that's the difference. You should know those. And the key word to this question is that we can ignore the curvature of the pipe. Now, let me draw out what's actually happening here. And annotate. Let's turn our color to red because I want to be able to see it. So in essence, this is what's actually happening. You have a pipe and you have insulation. The insulation is this part here that I'm shading. The pipe from the inside is a temperature of 200 degrees Celsius. And the temperature of the outside is 40 degrees C. Now, naturally, if you're not ignoring the curvature of the pipe, and we want to take a slice of this section here, we need to keep in mind that it's round shaped an object, and that will change our conduction equation. That will change our way of solving this overall. The key to this is that it's telling you that it is not round in shape. If you don't do that, you'll get the answer wrong first and foremost, and B, you'll make your life way more complicated than it has to be. So, if you remember in my favorite class with Professor Hamid, he told us that this is easy, or even in heat and mass transfer. This is easy. You have to represent it with log R1 divided by R2 plus log 1. It's a super complex equation that you guys would know instantly to use. It's even in the supply reference handbook, but it's just to throw you off. But remember, the key here is that we can neglect the curvature. So what you're really looking at is this. This is your 200, and this is your 45. And this would be your T1, and this would be your T2. Again, I apologize. I don't know why my thingy is being lame. Now, conduction that happens on the pipe of the wall, if it is not a round shape and we can neglect curvature, this can be described in an equation that's simple. Q dot equals negative K A delta T over L. Now you see what we have. We have K A delta T. We have a delta T, which is the difference between T1 and T2. We have K, which is a given, which is just going to be the K is a disgusting little 0.035, this guy. We have area, which they don't give us, and length, which is what we're trying to find. But more importantly, what is Q dot described as? Q dot is literally heat flux, and heat flux is defined by Q divided by A. And that is literally the heat transfer rate divided by the area. And the heat transfer rate can be described as H, temperature, and the difference in temperature, but the difference in temperature between the wall minus the difference in temperature of the infinity, in other words, of the surroundings. This is H multiplied by the wall minus the surroundings. Now, divided by area, which is good. Now let's erase this so we can. We know what Q dot is literally equal to. Now we can set and sub in what we have, negative K A delta T in this case is defined by the change in temperature in the wall due to convection. In other words, the change in temperature between T2 and T1. So this is going to be T2 minus T1 divided by L. Now, you might be questioning a couple things, like number one, area is in two places that you can't cancel it out. In essence, it doesn't matter as long as you make area the same thing on both sides. Area can be 10 both sides, area can be 1 on both sides, area can be 0. Well, actually, no, it could be any real number, not including 0. As long as the area is the same, they won't change the calculation. And for our simplicity, I'm going to say area is going to be equal to 1. I don't want to deal with it. And to make our lives even better, I'm solving for length, so that's easy. L is equal to negative K multiplied by the difference in the conduction, excuse me. This is conduction, the transfer heat between two touching mediums, conduction, divided by the transfer in heat between convection, which is between surroundings, and air, which is a fluid. And the infinity is the air. Now you have everything to plug in. You have K, which is negative 0.035. You have the change in temperature, which is 45 minus 200. You also have H, which is the combined radiation conduction coefficient, which is 12. And then you have the change in convection, which is between itself and a moving medium, which will be air, which is going to be the wall temperature. It's 45 and what's touching the air, which is going to be the 200, excuse me, not the 200, 30 degrees. This is going to give you an answer of 0.0029 meters, which is the same thing as saying 2.9 millimeters. Now, I can already hear the question, how do you know which temperature to subtract from the air? Well, if you look at your picture, the inside, this is inside the pipe. This 200 degrees is inside the pipe. There's not touching between the air. So that's not the temperature you'll ever use from the bottom. It'll do the 45 because that is literally, the surroundings are out here, which is 30 degrees as shown here. The surroundings are around it. Cool? Cool. Next question, 53. A nuclear reactor fuel tank consists of a metallic uranium cylinder 1.905 centimeters in diameter with an aluminum catting 0.127 centimeters thick. The fuel element is placed axially in a channel 3.81 centimeters in diameter. The coolant is water that enters at 80 at a flow rate of 130 liters per minute. The heat flux at a given point in the reactor is 3.4 times 10 to the 6 watts per meter cubed at the surface of the aluminum catting. If the flow rate of cooling water is doubled, the ratio between the old transfer and new heat transfer coefficient is most nearly blank. Okay, for this question, it's simple because it's on you to remember from heat transfer, the class, that if you double the flow rate of anything, you probably doubled the velocity, and you probably are going to double the Reynolds number. So if you double the Reynolds number, then you can have this simplistic way of thinking about it. There's H nu, which is the heat transfer coefficient, versus H no old, or divided by H old, is equal to, big parentheses, the new Reynolds number versus the old Reynolds number, to the power of a constant 0.8. Now remember what I said. If the Reynolds number versus the old number, if you're doubling the flow rate, if you're doubling the velocity, which if you're doubling the flow rate, you have to double the velocity, that means the new Reynolds number is twice as big as the old Reynolds number. So 2 divided by 1, it's a 2-to-1 ratio, to the power of 0.8. So this all, once you plug and chug, is equal to 1.7. So then it's answering the question immediately. If the flow rate of the cooling water is doubled, the new ratio between the old transfer and the new transfer coefficient is just 1.7. Boom. But that's an equation that you have to know and have to think about and remember and go into the reference manual if you don't see it, you know? Okay. Now 54 is super long, but it's a good question. Really good question, actually. I got it my first try and maybe happy. Okay. Waste heat is to be recovered from a 1.0 liter per second condensate stream using newly insulated countercurrent heat exchangers. Heat exchanger is a shell and tube heat exchanger with a single pass tube. That's good because that means if you remember heat exchangers, that's good because it makes it simpler. The condensate is to be cooled from 60 to 30, and a 10% sodium nitrate solution is heated in the heat exchanger and is being heated from 15 to 35. During the initial operation, the following data was compiled. The condensate data with the heat capacity and its density, the potassium nitrate with its heat capacity and its density, the tubing information, the inner diameter, outer diameter, tube length, number of tubes, the thermal conductivity, okay, and the individual heat transfer coefficients of the tube side and the shell side. And the question it finally says, what is the overall heat transfer coefficient of the system? All right. So it's a lot, but there's two things that you should never forget, and one is basic thermodynamics. You can describe anything happening from the system, from the heating side or the cooling side, with your favorite equation, Q equals mCp delta T. That describes heat change no matter what the system is. and they give you heat capacities of both areas and temperature differences and a way to find mass flow from both things. Now remember, another key important part to thermodynamics is that if you describe what happens in the condensate with this equation, you in theory also describe what happens in this stream with the same equation. The only difference is going to be the sign. Instead of it being positive, it will be negative, or it'll be negative, it will be positive, because it's the law of thermodynamics. It has to equal each other. You know, one is gaining and one is losing. That is how the heat transfer works. But it's the same number fundamentally. That Q on both sides is the same. Okay, undo. Okay. Now, with that said, we also need to think fundamentally, how do we describe an overall heat exchanger in a system? An overall heat exchanger is described by Q equals U, which is the thing we're looking for, the heat transfer coefficient, multiplied by A, which is the area of your tubing, F, which is the correction factor, because if a heat exchanger is more complex than a single tube pass, then there's a correction factor. In our case, it's a single tube pass, so we don't have to worry about the correction factor. It's equal to 1. And then delta T. Okay, so in my case, I chose to talk about the condensate and get everything in the right units, and then we use this equation, and then we use this equation. So let's start. What I mean by that. So let's calculate the heat loss or gained from the first part of the system, describing the condensate. Well, we knew that M we need to find, but M is given to you as 1 liter per second, and you can change 1 liter per second to you could change 1 liter per second to a viable form of meter cube per second, because remember, we're talking about Q and we're talking about SI systems. You really want to talk about meters instead of liters for a volume. So that's easy. Turn liters per second into meters cubed per second, and you're going to get 0.001 meter cubed per second, which is good because that is talking about volume. That is your volume flow rate. Now, you don't want volume flow rate, you want mass flow. And how do you turn a volume flow into a mass flow? Well, that's simple. You use density, and they also give you the density, which is 1 gram per centimeter cubed. But again, we have it in meter cubed, not a centimeter cubed, and we're using SI, and you don't want to use grams, you want to use kilos. So that is the same thing as saying 1,000 kilos per meter cubed. And that's how you're going to get a volumetric, a mass flow rate, not a volumetric flow rate. So multiply this whole thing by 1,000 kilos per meter cubed. Now we have M. That is M. It gives us the CP because we're lucky sons of guns. It gives you joule per gram per Kelvin. Now here's the thing. Again, you don't want this shit in grams, so convert grams to kilos and keep joules and Kelvin the same. If you do that, it turns into 42.00 joule per kilo per Kelvin, which is beautiful. So we have MCP, and now we just need delta T. Remember, delta T is just a change in temperatures. You don't have to change them into Kelvin. So we'll keep them as Celsius for now. And it's from 60 to 30. So simply do 30 minus 60. And that'll give you an answer of negative 126,000 joule per second, which is good. Now we have Q of the system. In that case, it's being cooled, so it releases energy to the system, which is good. Now, that describes Q. We have Q. We can find area. We described the F factor here being non-existent because it's a single pass tube. We don't have to think about a correction factor. And delta T here is not any old delta T. It is delta D log a mean temperature difference, which complicates everything, but is also easy to find. So we have Q. A, we can calculate simply using the area of a tube, which can be described as pi LDN. N stands for the number of tubes in the overall heat exchanger. Pi is a constant. The length is given to you in the tubing data, which is 1.8 in meters. And you want to talk about the outer diameter because that is the only part of the tube that matters. The overall diameter, 0.015. And you also want to include the number of tubes in the system, which we said is 54. This ends up giving you a nice little answer of, where did I put it? 4.54 meters cubed. A meter squared area. Now, we also need to talk about, we found A, we found Q, we need the log mean temperature difference. Log mean temperature difference will vary if it is a co-current or counter-current. Luckily for us, the question clearly states that it is, where is it? Counter-current heat exchanger. If you go to your reference manual, they give you an equation for a counter-current heat exchanger log mean temperature difference. And that is described for a counter-current as the temperature of the hot side that is coming out minus the temperature of the cold side that's coming in minus the temperature of the hot side coming in minus the temperature of the cold side coming out divided by the natural log of the first part of the term that we wrote out divided by the second part of that term that we wrote out. Now, it's the beautiful part to this. That is an easy equation to plug and chug, but it's on you to realize that we really, really, really should plug everything in. You don't need to turn anything to Kelvin because it's the difference, so it won't matter. It's temperature in Kelvin, temperature in Celsius, it's the same thing. You can convert to Kelvin, it just wastes time. So, let's write it all out. So the temperature of the hot side coming in is 30. Or excuse me, the temperature of the hot side coming out is 30, minus the temperature of the cold side coming in is 15, minus the temperature of the hot side coming in is 65, or excuse me, 60, minus the temperature of the cold side coming out, which is 35. Do the natural log of those two. So your log mean temperature difference, I'm going to just put delta LMD, is equal to 19.57. Okay, now we have everything we need. We have Q, we have A, F is equal to 1 because it's a single tube pass. Log mean temperature difference is calculated. I'm going to clear the screen. We have all our numbers, and you saw where we all found them. Rewind if you need to. Now, we're going to solve for U. And that's easy. U is equal to Q divided by AF log temperature difference. That's what that is. We calculate everything. The negative Q can stay negative. It can make it positive, but since we need a positive answer, turn it positive. It'll be 126,000 divided by the area, which is the 4.58. Correction factor 1. The log mean temperature difference for the system was 19.5. And if you plug it all in, you get a beautiful answer of 1405 watts per meter cubed times Kelvin. Super beautiful. That gives us the answer of A. All of that work you have to be able to do quickly, which is annoying. But it's not the worst thing in the world. Okay. So 55. 55 says a 50-inch centimeter ball, or excuse me, a 50-centimeter diameter steel ball is radiating heat to the surroundings at a rate of 73 watts with a surface temperature of 75. The following information of the steel is known. The following information of the steel is known, which is shown below. If ambient temperature is 22, what type of steel is the ball mostly constructed of? Galvanized, mild, stainless, and oxidized. Well, they're giving you data on emissivity, and you're going to be a smart son of a gun, and you're going to say, well, shit, I don't know what that is, because I didn't. And you go to your FE handbook, and you control F, emissivity, and it'll actually show you an equation, and the only one in the whole book, which is Q equals E, which is emissivity, sigma, which is a constant, where I'm pretty sure, where is it? It is a constant. I think it's the Boltzmann constant. I don't remember what constant it is, but it's a constant that is 5.67 times 10 to the negative 8th forever. That is what that means there. Multiplied by the area, multiplied by the change in temperature of T1 to the 4th minus T2 to the power 4. Beautiful. Okay, so it's easy. We have all the data needed. E is what we're looking for. Q is just 73 watts, because that is the energy, joule per second. Q is 73 watts. E is what we're looking for. Sigma is that 5.67 times 10 to the negative 8th. A is area. Area of a ball can be described with area of any sphere, which is a 4 pi r squared. And in this T1 minus T2, both of the power 4, you have to turn everything into Kelvin. If not, it doesn't work. So E ends up becoming Q divided by sigma A, the difference of T1 to the 4th minus T2 to the 4th. And if you plug everything in, the beautiful part is that Q is 73. Sigma is that 5.67 times 10 to the negative 8th. It is in the handbook. I didn't make this up. I wouldn't even know what it was. Area can be calculated, which ends up being 4 pi. I'm going to make everything easy. 50 divided by 100, because I'm going to turn that into meters instead of centimeters. Multiplied by 1/2 to turn it from diameter to radius squared. Now the difference in temperature, which is just turn them into Kelvin first, so add 273 to both temperatures. 382 to the 4th minus 295 to the 4th. All of this just then plug into your calculator, and you'll get emissivity as 0.237. In other words, it is galvanized. Okay. 56. 56 says, the overall heat transfer coefficient U for a heat exchanger has units of energy per time per area per temperature degrees. The inverse of the overall heat coefficient is known as R, thermal resistance. Which of the following is suitable for R? Okay, first things first, you need to know basic inverses. Basically, what it just told you is that U is equal to units of energy per area per temp, so just delta T, per time, like seconds. I'll put this for shits and giggles. R is the inverse, so you just literally flip it over. So it'd be area, temperature, time divided by energy. So that's number one. You need to know what exactly I just told you. And that is the units. So which of these are suitable? Well, immediately, if we're doing R, cannot have centimeters cubed on top. It cannot have seconds. It cannot have W on top. So your only two real answers are left are B and D. And seconds per meter cubed, or second multiplied by meter cubed times Kelvin divided by kilowatts seems like a good deal. But remember, we live in the world of SI. You don't want kilowatts on the bottom. You want regular watts. So this shit is trash. Heat squared times Rankine times minute divided by BTUs makes sense, because all of those in American engineering units exist and they work in tangent to each other. So the answer is D. Okay. Next one is 57. 57 states a double pipe heat exchanger is used to heat air. Air enters at 10 degrees C and it's heated to 90. This CP is that. The airflow rate is 75 kilos per minute, and the heat transfer rate W to air is most nearly blank. Well, again, I know it says heat exchanger, but remember, we can live in the world of thermodynamics where we can describe basically everything with it. The first equation that should pop in your head is Q is equal to mCp delta T. We have M, which is just m dot in this case, 75,000 kilos per minute. But remember, we live in SI. We can't use per minute. We have to turn it into seconds. So convert it. And for every minute, 60 seconds. Now CP is given to you in kilojoule per kilogram per Kelvin. Now that's good, but remember, we live in SI. You don't want to have kilojoules on top, turn that into joules. So you'll have 1.007 kilojoule kilo Kelvin. Turn that into SI units, so it'll be 1,000 joules per 1 kilojoule. All of that's being multiplied by a change in temperature, which is not that hard. You can keep it in Celsius. The same thing as the difference in Kelvin, 90 minus 10. Now multiply all three of these terms together, and you're going to get 1.007 times 10 to the 7th joule per second, which is the same thing as saying a watt. And the answer is going to be A. That is not what was supposed to happen. Now take clear. Okay. 58 is an easy question too. It says certain compact heat exchangers have small rectangular channels through which one or more heat transfer media flows. It is necessary to know the hydraulic diameter of the channels to calculate Reynolds number, initial number, and heat transfer coefficients for all configurations. For a given geometry, the hydraulic diameter is computed as 4 times the cross-sectional area divided by the wetted perimeter. Therefore, such a rectangular channel with 10 height and 4 has a width as a hydraulic diameter of most likely what? So the most important part of this question is actually just reading what it's telling you to do. It is literally saying that the hydraulic diameter, I'll just call that D, is equal to the cross-sectional area divided by perimeter. In this case, it's saying we have a rectangle, and the area of a rectangle should not be a surprise. It's just length times width divided by the perimeter of a rectangle, which is just 10 plus 10, because the rectangle has 2 widths and 2 lengths. 4 plus 4. This is what I just described is literally what it tells you to do right here to right here. And then D, even if you just do some basic plugging and chugging, will get you 5.7. i.e. A. If you guessed A on like the last 3 of these, you probably get a better score than me. Now, 59. 59 says, let's match the temperature profiles with the correct description. So the first one has T and L, and you'll first see that the hot fluid and cold fluid are both diagonal lines, and that should immediately scream to your face, counter current. When you have two lines looking just like this, it should be counter current. Counter, and there's no phase change. Bye-bye. The next one has a hot fluid going diagonally and a cold fluid going up. That should tell you co-current. Co-current. You know, this fucking pen let me write. Co-current. And there's no phase change. Now, life becomes really fun talking about these here at the bottom. For the next one, you have a hot fluid going diagonally down and a cold fluid going straight across. What the hell does that mean? Well, luckily for you, I have it written down so I don't remember. So, when the cold fluid is going diagonal and the hot fluid is, when the cold fluid is going straight and the diagonal is the hot, that is an evaporation stage. Evap. That describes evaporation. The cold fluid is evaporated as the hot fluid goes down in temperature. Now, as for the other one, if the hot fluid is a straight line and the cold fluid is diagonally going up, that is describing a condensation phase. Condensation. And then you'll realize that we have answered all of them, which is good. That is something you probably forever keep in mind. I didn't know that stuff before starting this, so that was cool to learn. Okay. Oh, this one's disgusting. Okay. 60. Liquid is flowing inside a tube coated with slightly insoluble organic salts having molecular weight of 250. The inside diameter of the coated tube is 5 centimeters. The following data is applied. Reynolds number, Schmidt's number, diffusivity of the salt, and the solubility of the liquid. After the boundary layer is established, before there's significant salt in the liquid, the molar flux is blank. Basically, find the molar flux. Okay. Now we're talking about a system that is liquid bulk flux. You go into your reference manual, you go Control F, molar flux, and you can describe the whole system. The beautiful part to this is that I already did that for you, so I won't make you waste time like I did in the last video going into that book and describing everything. So a liquid bulk molecular flux equation described as Na is equal to KL, which is just the mass transfer coefficient, divided by the concentration coming in minus the concentration touching the wall, which is normally 0. Now, they're giving you the Reynolds number, the Schmidt's number, the diffusivity constant, the concentration of the system coming in. We are missing the mass transfer coefficient. So how do you find the mass transfer coefficient? Well, the Schmidt's number, or the Sherwood number, is equal to, this is Sherwood number is equal to the mass transfer coefficient multiplied by the diameter divided by the diffusivity constant, which can also be equal to 0.0, a constant, 23, Reynolds number to the power of 0.8 times the Schmidt's number, 1/3. The question gives you Schmidt's, Reynolds, diameter, and diffusivity constant, which is Reynolds, Schmidt's, and diffusivity constant. You have to make sure you keep in mind that as long as the diameter is also in centimeters, you don't need to convert the centimeters of the diffusivity constant, and you can solve for Km. I'm not going to write it all down, but Km ends up becoming 3.19 times 10 to the power of -4, which is good. So we found Km. Now, Km is the diffusivity constant, that is KL. So we can plug everything in. So the diffusivity is equal to the number we solved for, which is 3.19 times 10 to the negative fourth multiplied by the change in concentration, which is that disgusting 2 times 10 to the negative fourth minus 0. This gives you an answer at 3.38 times 10 to the negative eighth. It's to the negative eighth because the units of this are moles per second centimeter cubed. And the question wants it in meters cubed, so once you convert the bottom to meters cubed, you get A. I don't like that question. In fact, I don't like anything that has to do with that shit. Okay, 61. It's a lot of words, but actually, this one's something that you learn in transport phenomenon. So it says, gaseous hydrogen is contained in a steel cylinder, 15 bars, 27 degrees C. Hydrogen can diffuse into a bubble defect of a cylinder wall, causing embrittlement and consequent failure. A defect is located 2 millimeters from the inner surface of the cylinder. The cylinder is considered large enough that the radial effects can be neglected, which is good. It makes life easier if we can think about things in rectangles. The system is now shown below. Molar concentrations of the hydrogen's inner surface is 1.5 kilomole per meter cubed, and initially 0 at the surface defect. The pressure of the inert gas is 1 bar, and the diffusivity constant is 0.3 times 10 to the negative 12 meters squared per second. If there's a linear concentration profile where established in the inner wall of the cylinder and the innermost edge of the defect before the concentration defect changed significantly, the molar flux of the hydrogen into the defect most nearly be blank. Okay. Well, luckily for everybody, that was a lot of words, but this is a liquid. No, excuse me. This is a gas-to-gas equimolar counter diffusion question. In other words, there's only 2 equations in that book that describe equimolar counter diffusion. That is Na equals dm multiplied by Ca1 minus Ca2 divided by delta Z. And delta Z is the change from the, it's just this, delta Z. There's no change, it is just distance. Ca1 is this guy, the concentration, and Ca2 is the concentration of the system at the wall. Easy enough. The concentration at the wall is always going to be 0 because there's no elements there. The concentration of H2 is given to you, and the diffusivity constant is given to you. You just plug and chug from there. So it'll be 0.3 times 10 to the negative 12 multiplied by the concentration, which was 1.5, divided by the 2 millimeters, which I'll turn into meters because everything needs to be in SI, so I'll divide by 1,000. And if you plug all that shit into your calculator, you'll get 2.25 times 10 to the negative 10. Which is C. Now, I just want to point out something really quick. You see how all of these has something in common? Negative 10 to the negative 10 to the negative 10. The only question that's not to the negative 10 is this negative 13. So if you're trying to guess, this is probably not the right answer. You have 3 options left to guess. Just a cool trick. Normally, the right answer is like mixed up in between all of them. Okay, so we got rid of page 1. Get that shit out of here. Okay, 62. The dimensionless Sherwood number is sometimes shown as a mass transfer Nusselt number and represents the ratio of convective diffusivity mass. Match the variables below to determine the relationship of the Sherwood number. Go into your FE handbook, Control F Sherwood number, and it's literally there. Write it out in plain daylight, and you just copy it. It is mass transfer coefficient, mass coefficient, mass transfer. I just don't want to spell it all because this pen is being asked. The mass transfer coefficient multiplied by the inside diameter of the tube. So tube, the tube D, the diameter of the tube, divided by the diffusivity coefficient. And it is written like S because the pen is being S. So it's the mass transfer coefficient multiplied by the tube inner diameter divided by the diffusivity coefficient, that is the Sherwood number. And you can control F it in here. You control F it in the old one, and you get the same thing. They literally tell you it. It's a nice 3 points. Okay. Oh, shoot. Well. So make that 3 questions I don't know how to do because I forgot to have these in my notes. Okay, so 63. So 63 and 64 and 47 I have not answered yet. Excuse me, I thought I was ready for this. Look at me. I must have got overconfident that they were tired and I didn't realize I didn't have these in there. So that's 3 of them that we still need to go back to. So I'll keep that in mind for the next one. So 63, 64, and 47 are the ones I need to go back to. Please excuse me. I didn't realize I did not have that in there. Okay. 65. We'll go back to those on part 4. Part 4 will be 20 plus 3. So it'll be a total of 23 questions that we'll go through. 65. The following data applies to a mixture of copper and silver at 500 degrees. D naught is 1.9 times 10 to the negative 5th. QD is 15,000 joule per meter. The diffusivity coefficient meters squared per second of the mixture is most nearly blank. Well, you'd be surprised, but if you go into your FE handbook solution manual, you can literally type in diffusivity coefficient and have a fucking equation for it, which is D equals D naught e to the power of negative Q divided by RT. And we have everything we need. D naught is 1.9 times 10 per second. E to the power of negative 15, 1, 2, 3 joule per mole divided by R, which is 8.314, multiplied by T, which is 500, but it has to be in Kelvin. So turn that plus 273. Okay. And then this is going to get you, once you plug all of that shit into your calculator, an answer of 1.4 times 10 to the negative 15. Easy enough. 66. In a continuous distillation column, the reflux ratio is the ratio of the distillate returned to the column to the distillate removed as product. In other words, in these, you have A, the fraction of total distillate returned to the column, kind of true, but not really. B, the ratio of distillate returned to the column as distillate removed from product. Damn, that sounds similar to what I said. C, ratio of distillate returned to the column to the total distillate. Or D, the ratio of vapor rate. That's the only one that's different, so that's immediately out. And the answer is B, the ratio of distillate returned to the column to the distillate removed as product. In other words, if you want to see it mathematically written, the reflux ratio, which I'll just call RD, is equal to L divided by D. In other words, it's equal to the vapor minus the distillate divided by the total distillate, which is literally describing in B. Okay, 67. I still can't believe I skipped all those. I'm so sorry. Okay, almost done with this one. 67. Saturated moist air, 1.2 kilos of water, that 50 kilos of dry air produces an air-water mixture with a temperature most nearly blank. Okay, so we want to figure out the saturated moist air containing. So what is the temperature of this air-water mixture? Well, sadly, there's this chart in the FE handbook that we have to go to. Didn't write down the page number, but it's called the ASHRE chart. Or I thought it was. There you go. This crap. That is not it, but it is close. ASHRE. It is in the thermal section of your book, which for some reason. There you go. Give me a second, guys. I might have misspelled it on my notes. It's this one. It is the ASHRAE psychrometric chart number 1. This is going to describe your saturation temperature, your dry bulb temperature, and the humidity ratio, which is very important to see. That is grams of moisture per kilogram of dry air. Well, in our case, the question says we have this mixture of dry to wet air. It is the humidity ratio, which is just going to be HR, is equal to the grams of moisture divided by the kilos of air. In our case, the grams of moisture is 1.2 kilos multiplied by 1,000. So let me write that. Because that turns into grams divided by kilos of air, which is just kilos of air, 50 kgs. This gets you a total number of 24. That is a humidity ratio, and we just followed what it says right here. So we have a number of 24. So let's zoom in. So we look at the if we look at the humidity ratio, 24 is right about here. Now let me make a nice straight ass line. Take that 24 and go straight across. That's cool. You hit the saturation temperature curve, which is cool. The issue is that the saturation temperature curve is not what we will have to actually describe. The question is asking us what is the temperature of the overall system? And if that's the case, we have to go down to the dry bulb temperature. That is the temperature of the system. That is not the saturation temperature. That is the sys temperature of the wet air moisture mixture thing. So it's between 20 and 30, and you guys can zoom in and you can count to be more accurate. But if you go back to our question, what are the answers? You have 17, which is out of the range, 47 is out of the range, and 89 is out of the range. Your only option left between 28 and 30 is 28. So that's the answer. And you circle that and you call yourself a day. Super annoying, but easy enough. Okay, 68. Give me a second, I need water. This is insane. '68 says wastewater treatment plants pump sludge slurry from a plant that is a rate of 55 pounds per hour at 38 solids. Sludge screws. The sludge goes through an incline of a screw conveyor that removes 67% of the moisture, followed by a belt press filter that removes another 89%, and the remaining moisture exits the screw conveyor. The moisture sludge then drops into storage bunk and transported to the landfill. The final moisture context of the sludge in the storage bunker is nearly blank. There's a lot of words. And I'm going to use this guy because I need more space for this one. So let's remove this and let's go. So it is saying that there is 55 tons per hour coming in to the system. It is 38% solids and it is 62% moisture. This is solid, this is moisture, which can then be written as 29 or 20.9 solid, those tons per hour, and 34.1 moisture. They go through an incline screw, where 67% of moisture is removed, and the rest of the solids come out. Give me 1 sec. Okay, so where were we? So we have 55 tons per hour coming into the system, where it's 38% dry, 62% moisture. So that ends up becoming 20.9% solid and 34% moisture. Something that's important, it goes through an incline screw thing that somehow removes 67% moisture. And keep this in mind, the solids go through just as solids. So 20.9 come out as 20.9 solids. The solids stay the same. Then it goes through a belt filter, or a bell filter, or whatever they called it. And they say this removes 89% of moisture coming through the system. And again, it's just removing moisture, so the solids mass stays the same. It becomes 20.9. So 20.9 coming in, 20.9 coming out, 20.9 coming in, 20.9 coming out. The only thing changing here is the 67% of moisture removed. So how much moisture is being removed from the system? For the first incline screw, 67% of the moisture is being removed. So that is 34.1 multiplied by 67%. And that gives you an answer of 22.84 of moisture being removed. So then you do 34.1 minus 22.84. That is what's coming out. And that is 11.25 weight of moisture coming out of the system. Now, in a similar sense, there's 11.25 moisture coming into the belt filter, but 89% of it is removed. So 89% times 11.22. That is 10.01 weight of moisture coming out from the top. So 11.25 minus 10.01 is equal to 1.23 of moisture coming out from the final moisture remover system. Now, the question is, what is the final moisture content? Final moisture content to this is pretty easy. It's just a mass percent. So you're going to do 1.23 divided by 1.23 plus 20.9 equals m%. We're calling that mass percent of moisture. And that equals, multiply this thing by 100, and that equals 5.59%. Now, if you go back to your answers, 5.9 is C. Beautiful. Or excuse me, 5.59% is C. 68. '69 states, equipment least likely to be used to make a gas/solid separation is electrostatic precipitator, centrifuge, cyclone, or baghouse. Okay, solid/gas separation should be an eye-opener number. A centrifuge removes liquid and solid. So the liquids stay on top and the solid goes all the way to the bottom. That's what a centrifuge does. It does nothing to do with gases. So B is the answer. 70. It says the angle of reports for various materials in a perfect cone-shaped pile is shown below. Which of the following materials have a cone taller than 14 feet and the material pile has a diameter of 48 feet? So the angle of reports is the maximum possible angle between the surface of a pile of powder and the horizontal plane. And this can be described using a tangent equation, which is the angle is equal to inverse tangent which is 2 times height divided by diameter. Now you have these numbers, which you'll just plug into that, which is tangent, or inverse tangent, mind you. 2 multiplied by 14 divided by 48 in diameter. And that gives you an angle of 30.2 degrees. Now, anything greater than 30.2 degrees will have a cone taller than 14 feet. And that will be not this, not this. So dry sand, crushed gravel, wood chips, all have a cone taller than 14 feet based on this equation, because all of those angles are greater than 30.2. Okay, now here's where the fun actually begins. And 71. The liquid reaction, the liquid phase reaction, A yields B plus C, the second order in A with a rate constant of 0.01 liters per mole second at 100 degrees, the initial concentration of A in the mixture, 25 moles per second. If the reaction is carried out in a batch reactor, the conversion of A is 80%, and the time in minutes is required for this reaction is most nearly blank. Okay. You see, Dr. Tamor would tell us to derive everything. I say fuck that and go to the back of the FE exam manual, go to the section of chemical engineering that says reaction engineering, and go to second order batch reactor liquid phase. They give you an equation that looks like this. XA divided by CA naught multiplied by 1 minus XA equals KT. Well, in this case, XA is equal to 80%. CA naught is the initial concentration, which is 25 moles per liter. T is time that we're looking for, and K is the rate constant of 0.01 liter per mole second. Now, the beautiful part to all of this is that everything is in the right units. You see how this is mole per liter, this is mole liter per mole second. Everything's given that we can solve for. So T is equal to XA divided by CA naught 1 minus XA multiplied by 1 divided by K. Plug in your numbers. It's going to be 0.8 divided by 25, 1 minus 0.8. Multiplied by 1 divided by 0.01. This gives you a T equal to 16 seconds, which is not B. You have to turn this into minutes, which is the same thing as saying 0.27 minutes, which the answer is D. 72 states, kinetic experiments were performed in a batch reactor based on reversible first order kinetics. A, forward reaction R, backwards reaction A, where R divided by A naught is 1.6, and the equilibrium conversion is 92% at 25, and the conversion is 60% after 4 hours. The forward rate constant in minutes is most nearly blank. There's a lot to remember, but if you look at a first order reversible reaction in the chemical engineering reference handbook, they give you a beautiful equation that looks like this. This equation is negative Ln 1 minus XA XE M plus 1 divided by M plus XE multiplied by KT, where M is this. Now, with all that being said, you can plug in chug as much as you want because XA is 60%, XE is 92%, M is 1.6, and T is 4 hours, and they want it in minutes, so turn 4 hours into minutes, and then solve for K. So just plug everything in, and it'll become 1 minus 60, so 0.6, divided by 0.92 is still ln, negative, equals 1.6 plus 1 divided by 1.6 plus 0.92 k multiplied by 4 times 60. Now solve for k, and it'll give it to you in per minutes, which is 0.00426. And the answer is A. Again, a lot of this stuff is going to the reference handbook and being smart and fast about it. Okay. 73, the rate equation, negative RA K1CA minus K2CB describes a series reaction. Well, no. Let me remind you that a series reaction is describing a reaction in steps where it's A yields B yields C. That is a series reaction. A goes to B, B goes to C. Where you can write two separate reactions, or you can model it as two separate reactions. A goes to B and then B goes to C. And the rate constant doesn't look like that. You'll have RB equals K1CA minus K2CB. That's for a series reaction. In a parallel reaction, it is A yields desired reaction and A yields undesired reaction, where you'll have two separate models for RD, which is the desired reaction, and RU, which is the rate of the undesired reaction. And the overall rate constant will be RA equals RD plus RU. In this case, that is also not being described here. An irreversible reaction is just something simple, where it'll be RA equals K1CA, which is not this. A reversible reaction describes it going forward and backwards, or I'll go what we're witnessing here. So the answer is a reversible reaction. Okay. 74 says, a study of liquid reaction is formed to determine the effects on temperature on the rate constant. At 40 degrees, K is equal to 0.5. At 70, K is equal to 1.1. At 100, K is most nearly blank. This should scream general chemistry. General chemistry in the case that you need to think about the Arrhenius equation. Arrhenius equation is the only way to relate two K constants to each other. And from the FE handbook, because I don't remember what the hell Arrhenius is E A equals R T1 T2 divided by T1 minus T2 ln K1 minus or divided by K2. Remember, you need to turn your temperatures into Kelvin. If not, this won't work. And you can plug and solve. You need to find EA. So EA is equal to 8.314 multiplied by both temperatures in Kelvin, which will be 40 plus 273, 70 plus 273, which is 313, multiplied by 343. T1 minus T2, which is 313, minus 343. ln of T1, K1, which is 0.5, divided by K2, which is 1.1. EA ends up becoming 2, 3, 4, 4, 5.2 joule per mole. Now you're going to use the same equation to relate K1 and K2 for 70 and 100 degrees, which is the whole reason we solved for EA. Now we can solve for K2, where K2 can simplify into using this same equation, and the only difference is that you're going to solve for K2. So it'll be 2, 3, 4, 4, 5.2 equals 8.314 multiplied by the new temperatures, which is going to be T1, T2, which would be 70 and 100, respectively 343, 343 and 373 divided by 343 multiplied by ln K1, which is what we have, 1.1 divided by K2. Get a little messy, but you can solve for K2 relatively easily. Multiply and divide all of this stuff out from the right side, then divide it all by 2445.2, take the exponential, subtract, take the exponential of both sides, and then solve for K2. If this right here is just basic algebra, if you need help with that, let me know. But people on the internet, same thing. This should be something really easy to solve for at this point. K2 becomes 2.13 seconds per second. 2.13, which is C. Okay, 75. 75 is annoying. I'll be honest. 75 says if if the oxidation of organic compound A produces 2 moles B and C by completing the reactions A plus O2 equals B, A plus O2 yields C plus D. This is a series reaction, a parallel reaction, because you're having desired product A and undesired product B and C, or the other way around, but this is a parallel reaction. If conversion of A is 80% selectivity, of B to C is 9. The number of moles of B formed per mole of A fed to the oxidation reactor is most nearly blank. So remember, selectivity is literally telling us here that for every mole of B divided by mole of C, so for every mole of B and every mole of C, it is a 9-to-1 ratio, which is 9. So if 1 mole of A is made, how many moles of B is made? Well, that's pretty simple. If 1 mole of A is made, then 1 mole of B is made. In other words, if only 80% of the reaction happens, then for 1 mole of A and the reaction only goes to 80%, how many moles of B are made? Well, for 1 mole of A and the reaction is 80%, how many moles of B are made? Well, first multiply everything by 1 mole of B divided by 1 mole of A. The 80% is how much of, so for every 1 mole of A, 80% of the reaction goes through. The stoichiometry tells us the 1-to-1 ratio. You'll get you're going to end up getting a total number. And excuse me, I miswrote something. Let me rewind. Let me rewind those steps. Let me reword. I'm sorry. So it goes like this. If 1 mole of A is made, how many moles of B are made? So logically, we're saying that 1 mole and 80% of the reaction goes through. How many moles of A do we have to start? The total amount of moles of A do we have to start are 0.8 moles of A. Note that if 1 mole of A gives both B and C moles, we can describe that as A, the 1 mole, gives us both 1 mole of B plus 1 mole of C. That is based on stoichiometry. So for every mole of A, 1 mole of B is produced. Every mole of A, 1 mole of C is produced. In other words, you could say for every mole, it is describing 1 mole of B and 1 mole of C added together. Now, we also can factor out this equation of C and now become B divided by C plus 1. The reason we're doing this equals A. The reason we did this is because we can describe now the system easily. We have A, we have 80% of moles that we're just starting out with. Where we don't know C, but we do know the ratio B to C is 9 plus 1, which is 10. Solve for C, and C gives us 0.08. Now, replug that into this part right here and solve for B. B gives you 0.72. So the answer is C. '76. The operating conditions for a plug flow reaction, elementary liquid phase reaction, A plus B yields R, are as follows. They give you all of this information, and they say, what is space-time for the reactor? Space-time for the reactor is described by delta, or tau, which is space-time, volume divided by flow rate. That is it. That is the definition of space-time. They give you the volume, and they give you the flow rate of the reactor, which is 0.5 meters cubed, divided by 0.2 meters cubed per minute. You plug them in. Space-time is equal to 2.5 minutes, which will give you D. Next question. 77. Compound A is a catalyst for a chemical reaction. Which of the following describes compound A? Well, compound A is a catalyst for a reaction which following. Compound A is recoverable at the end of the reaction. Doesn't sound like a catalyst. Or does it sound like a catalyst to me? Compound A is used as part of the reaction. Okay, maybe. Compound A permanently bonds to the one of the reactants, and compound A prevents the reaction. Well, okay. Prevents the reaction is the red giveaway. Catalyst does not prevent a reaction. Permanently bonds to one of the reactants also is a dead giveaway. So you're only working with A or B. Now remember, a catalyst makes the reaction time or lowers the reaction energy needed to make a reaction go forward. So in other words, it is not used in the reaction. All it does is lower the reaction time, and it's recoverable at the end of the reaction. So if you use a catalyst, you can reuse it again. Sometimes you can recycle catalysts or throw them away and buy new ones to keep lowering the reaction time. So the only answer here is A. Compound A is recoverable at the end of the reaction. Now the last question, thank God that I have written down, is the cost associated with building a chemical plant are shown below. Cost of land, total capital investment, fixed capital investment in year 1, fixed capital investment in year 2, plant, startup, working capital, and there's a graph, and it says which best describes the capital investment during year 2 of the process. So the little circle where it says circle and A, that first represents year 1, 0 to 1. This includes the cost of land plus the capital investment. So that circle line here, A, describes the cost of land plus the capital investment made up to year 1. In this case, it'll be 90,000 plus 10,000, which will give you about 100,000. Now, B represents year 2, 1 to 2 on the graph, and this adds year 2 fixed capital investment to the end of year 1. In other words, this is total represented capital. This includes cost of land, total capital investment of year 1, and total capital investment of year 2. Now C, this line right here from back to forth, that represents the depreciation period where you lose, money, you're depreciating in value. D, this up and down area, represents the total capital investment. And then from year 7, this little circle, that is the break-even point. And at 12, this giant line here represents the recovered capital, which includes the land value, the salvage value, and the working capital you'll get back after closing down your plant. So select the area of the graph which best describes capital investment in year 2 of the process. It's B because it describes year 1 to year 2, which includes capital investment for year 2, mainly here to here, in addition to all the investment you made in year 1, which is from 0 to 1. So the answer is this area here. That's your answer. All right, with that all said, so next video will be number. Oh, no, excuse me. One more before we do the next video. Finally, 79 says if 500 is invested in annual interest rate of 8% a year, its future worth at the end of 30 years would most nearly be what? This is an easy one where you need to. What the hell? This is an easy one where you need to realize that I is your interest of 8%. N is the number of years, which in this case is 30. And it's telling us what is the future worth of this material in 30 years. So the equation looks like this. Equals 500, its current present value, multiplied by 1 plus 8% to the power of n, which is 30. This gives you $5,031, which is this guy. And if you're curious where this equation comes from, go to your reference handbook, go to engineering economics, and it's the first one there. Okay. Now my voice hurts. This video concludes questions 48 through 79. I'm missing 63, 64, and 47. I need to go back and get those when I get the chance. Next video will conclude all of it from question 80 to 100 and the extra 3 that I'm missing. So, if any questions, let me know. If not, goodbye.